Welcome to the George Alcock Memorial Lecture. We are holding the meeting on Zoom and live streaming to YouTube. The recording will be available to watch on our YouTube channel a few hours after the meeting. You can ask questions by typing them into the Q&A on Zoom or the comments in YouTube, and we'll answer them at the end of the lecture. It's my pleasure to hand over to Alan Lorraine, the President of the BAA.
Thank you very much indeed, Andy, and welcome to everybody joining us on the BAA Zoom channel and also on the web, on the YouTube as well. And very much thank you to Jonathan Shanklin, our speaker this evening. But the George Alcock lecture obviously is one in memory of George Alcock, MBE. Died in 2015, I believe, but he was one of the most prolific amateur observers within the British sort of astronomical amateur scene, and finding his first comet in 1959, and then managed to find a further comet about 4 weeks later, which I think a lot of people go for an awful long time before they find their next comet. In total, I think he found 5 comets and nova as well. But one of the things that I remember Guy Hess telling me about him, who knew George very well, was his uncanny ability to watch the stars and to memorize the patterns, and to basically be able to recognize an intruder into those patterns. And that's the way he discovered his comets with his memorable binoculars. So this evening, to give the George Alcock lecture, we've got Jonathan Shanklin, former comet director of the BAA, but most importantly in this case, one of the members of the British Antarctic team, and he's going to be talking to us this evening, to understand, is with regards to his work with regards to the ozone layer and experiences down in Antarctica. So without further ado, if I can pass you over to Jonathan. Thank you very much indeed, Jonathan.
Okay, thank you very much. Hopefully you can now see my presentation screen. And I'd just first of all like to thank the BAA for giving me the opportunity to give a second George Alcock lecture. So I have already given one, and it's a unique, I think, achievement to be asked to give the second. And I've been asked to give more or less the same talk, but it won't be exactly the same. There will be quite a lot of differences. And I'm going to rattle through the slides at a fairly fast pace because there's a lot of them to show you. If I can persuade this to change, yeah. So the lecture is at least partly about George Alcock, and he was a noted BAA observer, and there are his trusty binoculars, which he used, I think, throughout his life. And the BAA arranged for a memorial to be put up in Peterborough Cathedral in his memory. So that's a really quite unique achievement for a modern amateur astronomer. And then there's me here in Antarctica, or at least sub-Antarctica, because this is the island of South Georgia. And George and I have discovered shared many interests, and I'll be telling you about some of those interests through the talk. George was noted for his comet observing and the exquisite detail that he drew in the tails of comets. And at the time, many people poo-pooed this, saying, no, you're imagining all that detail. But modern CCD imagery shows very many similar features to those that George drew. And it's very clear that some people have unusually acute eyesight that allows them to see this type of fine detail. As the President mentioned, he also was a noted seeker for novae, and this was one that he found disturbing the form of the coat hanger. And I'm sure he would have been observing the latest nova in Cassiopeia, here imaged by Nick James. But as well as his astronomical interests, he had many others. He was interested in wildlife and drew many exquisite sketches of the local wildlife around his Peterborough home. He was interested in churches, and I share an interest in churches, but I think his was mostly architectural, whereas mine is in ringing the church bells. And it's been really great this week to go back to ringing church bells after a long absence, because it's now permitted under the COVID guidance. Much of George's life was written up in this book by Kay Williams, which may still be available in the second-hand market, but it tells the life of an extraordinary gentleman. And a final shared interest was the Antarctic, because George participated in some scientific studies checking the difference between meteor rates in the two hemispheres. And at the time, it wasn't known what things would be similar and what things would be different. And study of meteors was one of them. He joined up in the RAF, and interestingly, my sister was also in the RAF. And for many of my trips down to the Antarctic, we would fly in an RAF transport plane via Ascension Island to the Falklands. And we'll see a little bit more of that in a minute. But my last trip down to Antarctica was flying from Cape Town to the Russian station Novorossiysk in one of the poshest planes I've ever been in. And this plane landed on wheels on a blue ice runway. And the worst seating in it was business class. So just showing where we're off to, here's a sort of hemispherical map. Ascension Island is this little point in the Atlantic, and then coming down to first of all, the Falkland Islands, across, usually by sea, in fact, only by sea to South Georgia, and then down to the Antarctic Peninsula, or Halley Station, which is just here. So first, flying over Ascension Island. It's a small volcanic island, not currently erupting, but who knows when it might start again. And George was certainly interested in volcanoes, and the book shows some of his sketches showing the eruption of Mount Vesuvius when he was based in the Mediterranean. And Ascension has many volcanic landforms, some of which may be shared by features on the moon. So this is a lava channel carved by flowing lava. And there are small imprints of volcanic bombs in ash that had already fallen. And locally, these are known as the Devil's Eyeballs. I'm sure George would have visited Mars Bay on the island, which is where David Gill spent 6 months observing the parallax of Mars at its close approach. And on my last trip down, we were treated to a short safari, some distance from Cape Town. And I'm sure George would have enjoyed seeing the large animals that you can see on that continent. So flying in the RAF plane to the Falklands, you pass over a windswept island with very few trees, certainly no native trees. And you might see from the air a number of atmospheric phenomena. This is the glory surrounding the shadow of the plane in the cloud deck below. Down on the ground is Stanley Cathedral, and in many ways the tower looks similar to one of the Northamptonshire churches that George sketched. If you're lucky, from the island, you might see noctilucent cloud if you happen to be there at exactly the right time of year. Very few people have been fortunate enough to see noctilucent cloud from the southern hemisphere, and I was exceptionally lucky on this occasion to see it. You have to be lucky because you need to be in that band between about 50 degrees south and 60 degrees south, for which there is very little occupied territory. Other atmospheric phenomena that George was interested in was the effect of clouds, and the lower of these two sketches made at Capri looks very similar to this Antarctic photograph, showing crepuscular rays streaming between clouds on the Antarctic Peninsula. At other times, you get the cloud drawn out into long wisps. This is cirrus cloud blown across the mountains of the Antarctic Peninsula. And the jet stream at these latitudes can be up to several hundred kilometers an hour. The mountains of South Georgia provide opportunity for another cloud phenomena, that of anvil clouds of one sort or another. And these stack of plates are created by the wind blowing over the mountains, the wind being forced to rise, and as it does so, cooling and therefore generating clouds. And in the same phenomena happens over the Rockies, and there US fighter pilots mistook them as unidentified flying objects, in part because if the wind is at a small angle to the mountain range, they can apparently move very rapidly along the length of the range. I think you would have to be very, very lucky indeed to see the dust trail of a fireball above Antarctica. This is one that I didn't see myself, but my colleagues on the Rotherham station were lucky enough to witness this decaying dust trail from a big meteor crossing the sky. And that brings me to another aspect of Antarctica, that it is or can be a great place for searching for meteors or meteorites. And that in part is because there are these chains of mountains. These are the Transantarctic mountains down here, and here is the spine of the Antarctic Peninsula. And where ice moving essentially from the center of the continent outwards comes up against one of these mountain ranges, it may be forced to rise. And this means that meteorites that have accumulated just about anywhere in the continent are brought to the surface in this ablation zone near the mountain range. And the Antarctic Survey over the last couple of years has been assisting some university groups to do meteorite recovery from the Antarctic Peninsula mountains. And what they've been doing is traveling on a skidoo, towing behind it a ground penetrating radar, looking for the echoes of small meteorites that are beneath the ground. Just occasionally they were lucky enough to find one on the surface, as in this example. The Antarctic continent is divided into various territories by claimant nations, but under the terms of the Antarctic Treaty, those claims are held in abeyance. Nevertheless, the claims are in part upheld by the individual countries both carrying out scientific research in their particular area, but also by having a civilian presence, which will usually be led by a magistrate who is appointed by the governor of the Falkland Islands, and also by running a post office. And those two functions are part of the continuing maintenance of a territorial claim. However, by and large, even though Argentina, Chile, and the UK share their territorial claims, they do so peacefully whilst in the Antarctic. And the area that I'm going to be particularly focusing on is what's called the British Antarctic Territory, this pie-shaped slice of Antarctica running from 60 degrees south down to the pole and between these two lines of longitude. We've got a small station in the Falklands and also 2 stations on the sub-Antarctic island of South Georgia. And we'll be looking at all of those during the talk. Traveling from the Falklands to other locations by ship can be a bit traumatic, but eventually you get into the pack ice and there the swell calms down and you start seeing people on board ship that you've never seen before because they've been kept to their cabins by seasickness. And down the coast of the Antarctic Peninsula, if you get calm seas, the scenery can be outstanding, with glaciers tumbling down to the coast and discharging lumps of ice. And as those glacial lumps of ice rock backwards and forwards in the slight swell, there's a sound like snap, crackle, and pop as you pour milk onto Rice Krispies. And it's the same effect, the little bubbles of air that have been trapped in the glacial ice, perhaps for millennia, bursting out into the atmosphere. Rather easier way to get from the Falklands to at least Rothera station is flying in our 4-engine plane, which can land on a gravel runway at Rothera. And from there, scientists can take off on wheels, but in flight transfer to skis that allow the plane to land deep in Antarctica. Life on a station can be fairly comfortable. This is the island of South Georgia, Bird Island. And in the summer, the air temperature can get to 5 or 10 degrees, but the sun is quite high in the sky, so the insulation is fairly good. Inside this particular small station, we were just a team of scientists, but nevertheless, on a Saturday night, you dress up and put on the best meal you can. And this was a Japanese-style meal that the team put together, which rivaled much that you can purchase in a posh restaurant in the UK. But as you get further south and have to do your work, life can get a little bit rougher, particularly when the temperature is far below 0. And so a short walk to where your science equipment is positioned may mean that you get rime deposited on your eyelashes, but once you get inside into the warmth, that will all disappear. And one amusing thing that is sometimes done is to throw a flask of boiling water into the air and watch it turn to ice crystals by the time it hits the ground. For relaxation, there's a lot of other things you can do. Skiing is quite a popular pastime, but it is important to make sure you put on sunblock on your arms and back of your legs, as well as on your face. And here I was doing cross-country skiing, which involves using sometimes what are called seal skins to allow you to walk up steep hills. But another type of skiing is what we call skijuring, where you're towed behind a snowmobile, sometimes at moderately high speed. I once had a bet with one of the mechanics that he couldn't drive the skidoo as fast as I was prepared to ski, and we sort of had a dead heat at about 100 kilometers an hour. But that was getting a bit too exciting for me. And on this occasion, it was much slower. It was only about 40 kilometers an hour. We have expert mountain guides on the station to supervise scientists when they go out into the deep field. And so they help you to rope up and teach you the necessary mountaineering techniques. So there is a convenient local crevasse that we can go down. And so there I'm all roped up with the climbing gear, wearing crampons and a helmet in case any of the crevasse collapses. On my last Halley trip, we did the same sort of thing. standing within a metre or two of the edge of what was originally called the Halloween crack, which started off as perhaps a metre wide. But by the time that I visited, it was getting on for 100 metres wide, and the ice cliffs in the background rise to 30 metres. And since then, the other side of that has broken off in a big iceberg. And finally, if you're feeling really tough, you can go for a short swim to the nearest ice floe, get your picture taken, and then dash inside for a cold shower, which feels incredibly warm, and it leaves your toes and fingers tingling for the rest of the day. It's also very popular to go looking at the local wildlife. And here's another sketch of George, of some of the birds on some of the pits near Peterborough. And so obviously the most well-known of the Antarctic birds is the penguin. This is the king penguin, which I think is probably the most attractive of them all. Within the background, a mix of fur seals and elephant seals. I was lucky enough to be on Bird Island, where there are a variety of albatrosses. I think this was a young black-browed albatross. But when I was there, the great wandering albatrosses were busy incubating their eggs. And just as I was leaving, one of them started to hatch. And that was a really amazing sight to see. You also get to see, if you're steaming down the coast of the Antarctic Peninsula, some of the great whales. This is a humpback whale just starting to dive down, and some of the seals popping up through holes in the pack ice. So back to some of George's interests. And he was a noted meteorological observer, as well as an astronomical observer. So he was very interested in weather and climate. And Antarctic weather can be quite extreme at times. When the wind is blowing 30 knots, the bamboo flags that we use both to mark routes across the ice, but also to help indicate the wind speed, are starting to bend double, and visibility is reduced to just a few meters. Under those circumstances, there is no travel, and you just have to hole up in your tent. But when the wind calms down again, you might see interesting meteorological phenomena. And this is a fog bow caused by a very thin band of fog across the scene there. And it's formed in exactly the same way that a rainbow is formed. But because the droplets are so small, you get constructive interference back again. And instead of seeing the rainbow colors, you see the white bow. You do occasionally see rainbows in the Antarctic, particularly along the Antarctic Peninsula, where summer temperatures can be typically 5 to 10 degrees when it's really warm. But more importantly, you do get the ice crystal phenomena of various halos. And here is a display where there are the 22-degree halo, the 42-degree halo, the upper arc of contact, various other arcs of contact, the two parhelia on the 22-degree halo, and a circumzenithal arc running all the way around the horizon. And very often, although you can see displays like this in this country, those of the Antarctic are much more intense, simply because of a phenomenon called diamond dust. And when the atmosphere is very cold, usually below about -15 or so degrees, water vapor can condense directly to crystals, and these crystals fall out of the sky. And as they do so, they catch the sunlight, glistening like millions of tiny diamonds descending from above. You can also see sometimes halos in the snowpack, if it's developed a particular crystal structure. And here is the 22-degree halo, showing very clearly the dark interior to the halo, which is caused by the light being scattered out of that particular band. Mirages are another phenomena. Here at Halley, there's a distant ice flow being elevated into enormous cliffs. And on the right-hand side of this image, you can imagine a castle in the distance. And that sort of miraging is known as Fata Morgana, after the Arthurian enchantress who could supposedly conjure castles out of thin air. Sometimes the miraging can create apparent mountain ranges. And this is at Halley, where there are no mountain ranges in view. And that is just sea ice and open water being amplified by the air near the ground, acting as a lens to create seemingly a mountain range in the distance. And then as the final fragment of the sun sets below the horizon, if you're really lucky, you might witness the green flash. This is a photo from the American pole station, where on occasion they've seen the green flash for 24 hours on the run. On my last trip, as we were leaving Antarctica, I noted that it was a really nice, clear day as the plane took off. So as soon as we were allowed to unfasten the seatbelts, I got to a window and looked out, and I was rewarded as the final fragment of sunset with a bluey green flash as the sun disappeared over the sea. Looking in the other direction, you might see a different phenomena. And in the gap between the two mountain peaks, you can see faintly in the distance some more mountains. Those are about 100 kilometers away, which gives you an idea of the clarity of the Antarctic atmosphere. And this grey band in between the two peaks is in fact the shadow of the Earth rising up. And if the circumstances are just right, as they were earlier today, they might intersect with the moon and create a total or partial lunar eclipse. As it gets darker, we might see some familiar constellations. Here is Orion doing a handstand on the ice cliffs at Rothera Station. But if you go somewhere where it's truly dark, and at Bird Island, when I was there, we would switch the generators off at night to save fuel, then the stars shine forth in all their glory. And here we've got the southern Milky Way arcing from horizon to horizon with the Southern Cross and the Coalsack Nebula and the two Magellanic Clouds. And perhaps a satellite or a meteor trail in the background there. Certainly I never saw it at the time. Comets are seen from Antarctica from time to time. Unfortunately, the last good one that occurred whilst I was there, I didn't see because I was too far south. So Comet Lovejoy put in a spectacular view for astronomers in Australia, but I was well south of the Antarctic Circle with 24 hours of daylight and unfortunately never got to see it. Today, most of the weather observations are made by automatic systems, and this is one of the ones that we use. It has a solar panel to charge up batteries to provide power through the winter, a propeller-driven wind vane to measure wind speed and direction, a sensor to measure snow depth, a temperature sensor, a transmitter to send data up to a polar orbiting satellite, and in here, a barometer. And those same polar orbiting satellites are imaging what goes on below. And this shows a typical midwinter false color image where surrounding Antarctica is pack ice, which has effectively doubled the size of the continent. The center of Antarctica is very often cloud-free because here we're at heights above 3,000 meters and the storm systems that surround Antarctica cannot penetrate that far and high inland. And it also shows that the passage between South America and the Antarctic Peninsula has no land around it at all. And that's why this is the Sirius 60s, one of the stormiest ocean passages in the world. When we average the daily temperatures over complete months, we see something of the yearly climate pattern. And certainly whenever I would leave for Antarctica, people say, oh, it's going to be incredibly cold. But you can see that Cambridge winter temperatures aren't that different from South Georgia summer temperatures. Rather, our summer temperatures are a bit colder. Halley averages about -5. And indeed, when it gets above freezing at Halley, it's rather unpleasant. And -10 is about right. Halley can drop to -30 on average during the winter and does drop down to -50. But because it's a coastal station, it doesn't experience the really seriously low temperatures of Antarctica, such as the Russian Vostok station, where if you go outside when it's really cold, you effectively have to put on a spacesuit in order to survive. And there they've recorded the lowest temperature anywhere on the planet Earth of -89.2 Celsius. We might think that April and May has been exceptionally cold here in England or UK and Western Europe. But in fact, when you look at the global context, which is very important when assessing climate change, we can see that this was a rare exception to the global pattern where most of the planet has been experiencing either record warmth or much warmer than average temperatures. And these regional patterns are quite important for perception of climate change. So in the region of the Antarctic Peninsula, South Georgia, the Falklands, and the tip of South America, a broadly similar pattern has been seen since measurements started, with a cooling until the 1920s, and then either a slow or more rapid warming since then. And since about 2010, some of that warming seems to have slackened off a little bit with a bit of a plateau, but who knows when that will resume. So we can't always blame temperature changes just on what we're doing, but we'll see a little bit more about that in a minute. What is obvious for the Antarctic Peninsula is the change in the ice cover. The ice in many areas is melting and retreating. And when you fly over a glacier in the summer, you can see many melt pools. A lot of glaciers are in retreat. A few are advancing, but on occasion, an advancing glacier is still in trouble. It's just that its bed has been better lubricated by that meltwater, and therefore it's flowing more quickly towards the sea. Along the east coast of the Antarctic Peninsula, several ice shelves have broken up in the northern reaches. First, this one called Larsen A, then Larsen B, and more recently, part of Larsen C, although the thought that broke up more through natural forcing than through climate change. It certainly has made the news with the large fragment getting as far as South Georgia and then splitting up into many smaller lumps. And all of them have now shrunk to a size where they're not being individually named. Climate changes on a variety of timescales, and on a decadal timescale, much of that forcing comes through the ocean currents. And that may well be what is happening over the Antarctic Peninsula region at the moment. It is these ocean currents that is changing things. Another thing that affects climate are volcanoes. This was a small volcano that erupted over the Antarctic Peninsula in the 1960s. A rather larger one was Mount Pinatubo in the early 90s. And this put sufficient material up into the stratosphere that it led to a global cooling for a few years. But that material fairly quickly falls out of the atmosphere and warming then resumes. And then there is the sun. We know the sun is a variable star with sunspots on its face. And this looks actually remarkably similar to what we have at the moment, but this is a slightly older sequence that I put together, if it will behave itself. And hopefully you can see the sun rotating and sunspots both persisting through a full rotation, but also some sunspots forming and disappearing on much shorter timescales, along with the surrounding faculae. And the number of sunspots goes up and down in a roughly 11-year cycle, and the latest cycle is just starting. Now, at one time, people who didn't believe in man-made climate change were saying, well, look, between 1900 and 1960, the peak of the sunspot cycle has been getting bigger, the climate's been getting warmer. That proves that it's entirely due to the sun. Unfortunately, of course, since then, solar maximum have dropped, but the climate is still getting warmer, which really rules out the sun as a significant driver for the climate change that we're seeing. And that really leaves us, through agriculture, industry, and transport, increasing the amount of carbon dioxide in the atmosphere. And this is recent measurements from the Mauna Loa Observatory. We have been doing similar measurements from our Halley station in Antarctica. And this last Antarctic summer, that work has been automated and hopefully will run through the Antarctic winter. But if we want to see what's been going on further back in time, we can look at the ice of Antarctica. And in this big tabular berg, you can see layers in the ice, and those correspond to annual layers. So just like dating trees, you can date ice by counting the layers as you go down. So our glaciologists will take a mechanical drill out an ice core, which is then analyzed in the lab to collect the gas that has been trapped in the ice, and also measure the oxygen isotope ratio in the melted water, which gives you a proxy for the temperature of the snow when it fell. And when you plot this up over hundreds of thousands of years, the deepest core that's been taken so far goes back about 750,000 years. One of the objectives is to go back 1 million years. But here I'm just showing the last glacial period. And you can see that temperatures come out of a glaciation fairly rapidly and then slowly fall in and come out again. And then at this point, the scale changes to show the last 1,000 or so years. And here's where we are now. And there's two particular points to notice in this. Just how far above we are a typical interglacial compared to a glacial period. And that between glacial and interglacial is maybe 10 degrees. So perhaps in the long term, we are storing up a 10-degree rise in temperature. But we only talk about what is going to happen in this century, and we're on track for a 2-degree rise or higher. The other point to notice is we're doing in 13 years what nature took 1,000 years to do coming out of the last ice age. And so the ecosystems around the globe are unlikely to be able to cope with such a rapid transition. So I'm going to finish with talking a little bit about the Antarctic ozone hole, a topic which I'm sure would have fascinated George. And I'm going to try and answer the question of, do we have an exceptionally large ozone hole today? Is it safe for penguins to go sunbathing? So what is ozone? It's a form of the oxygen gas that we breathe in the air, but instead of having 2 atoms, it has 3, which makes it a lot more reactive. It's made from oxygen in the air by the ultraviolet light in sunlight breaking apart oxygen molecules to give oxygen atoms, which then react with oxygen molecules to make ozone. And most of that process happens at high altitude, above 40 kilometers over the tropics. And the discovery of ozone and the ozone hole is very often, as is the case in science generally, a series of complete accidents. And ozone was discovered by a Swiss-German chemist who was experimenting on passing an electric current through water to make hydrogen and oxygen, because he knew that was what water was composed of. However, he noticed a funny smell. And so he followed up on that funny smell and found that he'd made this new gas called ozone. It's often said that this is what you can smell when you go to the seaside, but it just so happens that ozone and rotting seaweed smell very similar. Another step in the discovery of the ozone layer came when astronomers used spectrographs to look at the spectra of stars. And they found that there was a cutoff in the UV at about 280 nanometers. And it was known from simple physics that light ought to be emitted at those wavelengths. And so it was postulated that there must be something in Earth's atmosphere that was blocking the transmission of that light to the surface. And today we know that ozone mostly exists in a band between about 10 and 30 to 35 kilometers above the Earth. But even in that ozone layer, there isn't actually that much ozone present. If you brought it all down to ground level, you'd have a layer just 3 millimeters thick of pure ozone. And in many ways, the next step in the story was not an accident. It was a deliberate scientific endeavor by a professor of physics at Oxford University, who designed what is still one of the world's standard instruments for measuring ozone from the ground, the Dobson ozone spectrophotometer. And it was Dobson that suggested that some of these instruments should be sent to the Antarctic when the Royal Society sent an expedition there as part of the International Geophysical Year in 1957-58. And this was that first Halley station being set up. My first Halley station was the third in the sequence. And this is me when I was much younger, measuring ozone using the instrument at that station. More recently, at the 6th Halley station, we've got a purpose-designed observing deck where you can observe in quite good comfort. And in fact, the whole of this science module of the complex, the outline was designed by me to give a really good all-round view for the meteorologists observing the weather, and also for comfort in using the Dobson instrument. It was named after the Edmund Halley that we all know and love, most famous for his comet. And I was lucky enough to see that in 1986 over the mountains of the Antarctic Peninsula, being the first to see it from Antarctica and watching it rise tail first, which was quite a sight. But as well as comets, Halley was interested in many other things. He was interested in the meteorological phenomena that I've been discussing. He was interested in the Earth's magnetic field. He was interested in aurora. He was interested in tides, and all of these things were to be studied at the Antarctic station. Halley had also been a secretary of the Royal Society, and it happened to be the 300th anniversary of his birth. And this is what the scenery at Halley would look like roughly at the moment at midday. Halley is in 24 hours of darkness, not total darkness, but certainly there is no sun from early May through until August. But there are other lights in the sky. The first sign of an auroral display that you might see from this country are the pale smudges on the right of this screen, because generally here the aurora does not get very far up. But as a display develops, you might see the auroral curtains in the distance, and then the aurora moving to overhead, where it can be stunningly spectacular. And I've seen it a couple of times myself from dark skies around Cambridge. Sometimes it takes weird forms, and you can almost imagine that this is a ghost or a dragon flying through the sky. And that may be where some of the Norse myths and legends arise. The Vikings would look up in the dark sky, see moving figures that they interpreted as living creatures. And my last journey to Halley was caused because of, first of all, this Halloween crack, which I mentioned earlier, but also these chasms, which were blocking any safe route to Halley Station, which also might be about to float out as an iceberg. So the station was moved, as it was designed to a new site, and I went down to be a meteorological observer. And that was really quite fun because I had no administrative duties, and I could just do the day job of observing the weather, and then in the evening, if there was time, going out skiing. But when I first joined the survey, there'd been concern that the exhaust gases from Concorde or spray cans containing chlorofluorocarbons might damage the ozone layer. And being a naive young scientist, I thought that must be total rubbish. I know, I'll show people that there's nothing going on. And in part, my naivety came from the very complex atmospheric chemistry. And being a physicist, I didn't really thoroughly understand chemistry. But one of the key predictions was that this chlorine catalysis would take place using this chain, and that could only happen above the equator at high altitude. But eventually I was able to persuade my bosses, Joe Farman, Brian Gardner, that something really was happening. And that led to us publishing in Nature what is now one of the most referenced environmental papers ever, showing that as CFC amounts were increasing, so ozone amounts in the spring were declining over our Antarctic station. That decline continued until the 1990s, and since then there has been a slow recovery, but there is still a long way to go before we're back at our starting point. Why does it happen over Antarctica? Simply because during that polar night, temperatures fall below minus 78 degrees Celsius, and that allows clouds to form in situ in the ozone layer. These are known as nacreous clouds or mother of pearl clouds, or sometimes stratospheric clouds. They're incredibly beautiful, but it's also on those surfaces that chemical reactions take place that convert the chlorine into an active form, so that when the sun comes back in the Antarctic spring, ozone is destroyed about 1% a day. And this movie just shows this year's ozone hole forming, covering the entire Antarctic continent, occasionally spinning north over the Antarctic, to the tip of South America, never covering Australia, and then filling in during the Antarctic summer. When the ozone hole is around, we have to take significant precautions against sunburn, because you can be burnt in 5 minutes or less. Today, thanks to the Montreal Protocol, release of those substances into the atmosphere is banned, so that when old fridges are scrapped, their contents are recovered and burnt at high temperature to destroy the CFCs. But as I said, even though the Montreal Protocol has been signed by all UN member states and is working, the recovery is going to take until 2060 or 2070 before we're back to square one. And that assumed that everybody was following the protocol, and measurements from the ground of CFCs showed that they weren't falling quite as rapidly as expected. And this was traced to factories in part of China that were carrying out illegal manufacture. We think that has now been shut down by the Chinese government, who were probably unaware of it. One question is, why over Antarctica and not the Arctic? The answer is essentially because the Antarctic is a mountainous continent surrounded by an open ocean, where the Arctic is an open ocean surrounded by mountainous continents. And that means that the atmospheric circulation over the two hemispheres is very different. Over the Arctic, it is usually much more mixed, and that means on average, it is much warmer by about 10 degrees, so that stratospheric clouds are rare, but not impossible in the Arctic. Just on occasion, they do form, and I've been lucky enough to see them twice from Cambridge. This was a display in 1996, but just a couple of years ago, there was a significant area of ozone depletion above the UK and Western Europe, and that was caused by stratospheric clouds, which were seen from this country. Finally, just a point that although climate change is usually seen as warming the surface, higher up there is a cooling. And you can see that this cooling is punctuated by some of the big volcanic eruptions where there is a warming, and that's just the reverse of what is happening at the surface. So the surface volcanic eruptions produce a cooling, higher up it's a warming. Overall, however, it is a very complex system with many interactions between air, sea, and land. And so having a precautionary principle where we don't put things into the atmosphere until we're absolutely certain of the effects is by far the best practice. George went to the palace to receive one of his medals from the Queen. And I was lucky enough some years ago now to receive the Polar Medal from Her Majesty, and took my father and sister there as guests. And it really is a great honor to have been awarded that for the work that I've done in Antarctica. So that brings me to the end of the story. I hope that has entertained you, educated you, and also shared both some of George's story and some of my own story. Thank you very much.
Thank you, Jonathan, for a fascinating talk. It's really interesting to hear about your personal time in the Antarctic. Must be an absolutely amazing place. Just to let everyone know again, if you want to ask a question, you can use the Q&A in Zoom or type in the comments on YouTube, and then I'll keep an eye on both. We do have a question from Darryl Dobbs, and he's asked, do you measure the abundance of krill and its impact on the wildlife?
That's not something I do, but it's certainly something that our scientists do, particularly around South Georgia and from Rothera. And one of the concerns had been that the big iceberg, if it went aground, might prevent penguins from traveling to their feeding zones. And one of the uses of new technology that we've been doing is both for penguins, for seals, and for albatrosses, attaching small transponders to them, which measure where they're going, how long they're spending feeding, how deep they dive, and things like that. And that shows the main feeding grounds. And certainly around South Georgia, this showed that they were using some particular feeding grounds that weren't being regulated by the fishing protocols. So they've now been brought in as a result of this scientific study to allow some no-fish zones, some additional no-fish zones. So the fisheries around South Georgia are probably one of the best managed in the world because the fishery is informed by the science and not by the politics.
Thank you. And was I right in hearing that some of the measurements which used to be sort of made by hand are now being automated?
Yes, our Dobson spectrophotometer has been automated very cleverly by some of our engineers and now runs completely unattended after its service in January through to the following January. So we get continuous measurements and actually much more frequent measurements than a human observer could possibly do. It effectively makes a measurement every few minutes. And having tried that as a human observer, it is completely mind-blowing and you can't keep doing it. And so this is one area where, although it's essentially using exactly the same technique as Dobson designed in the 1930s, it's doing all those measurements mechanically by itself. The data is being logged on computer, and provided our SATCOM system is working, I can get it on the desk within sometimes minutes of it being made.
And do you think in the long run, will this mean that researchers travel to the Antarctic less, or is it going to be that actually they'll go there anyway? It's just there'll be sort of the more continuous measurement.
I think we'll always need engineers going to the Antarctic to service the equipment, but also you do need the scientists to be there to interpret what the instruments are giving. Because for an engineer, something may be working perfectly, but if it's giving rubbish data, it's the scientist who will spot why it's giving rubbish data. And as an example of that, there was one occasion when one of the engineers came to me and said, John, the instrument's not giving any sensible data. So I thought, okay, I'll go and have a look. And I had a look round. And they'd forgotten to open the hatch in the roof that let the light into the instrument. So yes, it was working perfectly, but it wasn't getting any data from the sun, which is what the light source is, to do the measurements.
Yes, it can sometimes be the simple things which are what trip things up.
I think in my experience, it's more often than not the simple things that have gone wrong, not the complicated things.
Yes, don't make assumptions as to what's causing the problem.
Yep.
Right, well, in just a moment, we'll hand over to Nick James for the Sky Notes. I'll just give a brief plug because we've got our next Wednesday webinar at 7 p.m. on the 9th of June, and that's going to be Sketching Deep Sky Objects by Howard Banish. There's also a radio astronomy section, Zoom, on Friday, May the 28th at 7:15. If anyone's interested, you can get the details on the website and also how to contact Paul Hearn to join that, because it's not being done as a webinar. You have to contact someone to get a link sent to you. Thanks again, Jonathan. A really fascinating talk. And hopefully one day in the not too distant future, we'll be able to meet up again in person somewhere.
Yeah, that'll be good.
Yeah, it was really good, John. And I always used to be, when you were comment section director, it was always good when you were down in Antarctica because you would always manage to find time to do all those comment section reports.
And on the early trips, type in all the handwritten data from the record cards.
Yeah, yeah.